Hi everyone. Yeah, so today I'm going to talk about hardware security. It's not that hard and it's not that secure. So, I feel like the best way to always start one of these things is like an XKCD comic. I like this comic because it's kind of double-edged here. You could use it to either justify hardware security or speak against hardware security, right? Like, because the point of the comic is that a system is only as secure as its weakest link, right? If you're pro hardware security, what you'd say is, well, if the hardware is not secure, how can everything else that sits on top of the hardware ever hope to be secure? The counterpoint to that, of course, is that if you look at all like the major security exploits in the past however many years, they're all like software based. They're all like buffer overflows and remote code execution and nothing to do with like faulty hardware. So maybe I should have put it at the end. I shouldn't have undermined the talk right at the beginning, but let's pretend I didn't say that. So what does it even mean to be secure, right? You're in this class, you probably know. A lot of encryption particularly relies on like the hardness of certain math problems, right? So for instance, RSA relies on the fact that like factorizing integers is hard, particularly like if you have a really big multiplication of two primes, it's hard to find out what the prime factors are. And that's like the key to RSA, right? For Diffie-Hellman key exchange, it's computing logarithms is hard, right? And that's what makes that secure. For like lattice-based cryptography, the idea is that finding the shortest non-zero vector in a lattice is hard. That one's a little bit of a mouthful, but the nice part about that one is that one's supposed to be like post-quantum secure, right? Other encryption schemes, they don't really rely on like any particular math property. They just rely on the fact that, as far as we can tell, you can't do anything better than like brute force guessing. Think of something like AES, right? If I give you like a ciphertext and a key, a ciphertext and a plain text, there's really no clever trick you can play to get the key. You're just gonna have to keep guessing, and that's kind of how that's what makes AES considered secure. If you can't do better than brute force, it's secure. And then there's a lot of like practical security methods. Whoopsie daisies. All right, and a lot of practical security mechanisms. This one seems probably more what you guys have done. You just try to block you from doing anything you're not supposed to do, right? Like Windows does it. It's like you can't change certain settings unless you're administrator or something like that, right? So there's like a lot of different like ways to like use the word secure, I suppose, right? But regardless of your definition, like a lot of guarantees, like they only kind of like exist in the mind, and by in the mind I mean sort of like on pencil and paper as well. Right? The real world is never quite as ideal as you'd hope it to be, and that's sort of how you're going to get the rug pulled out from under you here. So as a great philosopher once said, nobody's perfect, right? And that includes certain computer systems. So imagine you have a black box system, all right? You take some plain text, you get a key, a secret key, I should add, and you get a ciphertext out. And assuming that this is actually like a secure mechanism, what you get out essentially looks like random noise, right? There shouldn't be any really discernible pattern to this thing, right? The idea is that it's secure if given the, just looking at the random noise, an adversary shouldn't be able to deduce the the plain text or the key, right? But again, this is a very idealistic scenario. What really happens is that when you compute on the ciphertext and the key plain text and key to generate the ciphertext, you sort of like leak some information here, which I've decided to depict as heat dissipation. And you get out this random noise, right? And again, the adversary, you assume they can see the ciphertext, right? That's just sort of a given. But they can also sort of see this extraneous information generated through the thing. And again, they can't see the key, they can't see the plain text, but this is basically how side channels work, right? It happens when the adversary learns something that they theoretically shouldn't have because the implementation is broken, right? And this basically just happens whenever the behavior of a program varies due to the input, right? So again, let's take some system, you throw in some inputs, and you get output that basically looks like random noise, right? But let's say you throw in a blue input, you throw in a red input, right? And again, this is like sort of a leaky system, right? Say that like, I don't know, it glows the color of the gem that you put in, right? Now we have a similar setup. The adversary doesn't know what gem was put in, but they do see the output, right? But they also see, kind of what color the box glows. And even though they don't know what the plain text here is, through like the side channel, the extraneous information that they gathered, they can deduce what the input was, right? And again, this is sort of like, I think, a very easy cartoon example. It's a little trickier in practice, but this is, I think, this is how it works in a nutshell. And so, you know, we don't really have gems and glowing boxes in the real world. Your side channel is basically going to be timing, right? So a little bit more realistically, what does it look like? Again, you have like some system and you pass in 2 different inputs and you get some random noise. What really will be different based on the input is the time it takes to compute, right? So maybe if you throw a blue gem into this system, it goes quick. You throw a red gem in the system, it actually takes a long time. So now what the adversary does is they walk in with a timer, and they see that, okay, you've put in a gem in the system, and I know that I see the output very quickly. You must have put a blue gem into the system, right? And so this is how like sort of like a timing-based side channel works. And I guess moving a little bit past the cartoons to a slightly more sophisticated cartoon. Have you guys covered like timing side channels? Okay, great. Well, then this will be a fun little segment. Let's look at this horrible password checker, right? So let's walk through it step by step. It's pretty simple. So the first thing you do is you get the username and password from the user, right? Next thing you do is you get the real password from a database, right? You use their username, you get the real password. And what you do is, well, first thing you want to do is you want to check the length, right? You want to make sure that, okay, I mean, if the password's 5 characters and they enter 10, it's probably not the right password. Go ahead and exit. And then finally comes like the meat of it, which is just, you just loop through both the guessed password and the actual password, check them character by character, and if at any given point the characters mismatch, just go ahead and terminate and say, hey, you got the wrong password, get out of here, all right? Now, why is this a terrible password checker, right? And you know, maybe I'll open up to the floor, I guess. Yeah, so early termination means the amount of work the program does is a function of how many characters match, right? That's going to be a problem. How would you break it? Well, let's say you stumble upon your friend's phone, right? And you're not a good friend, so your first thing you think is, I'm going to go ahead and crack it. And your friend's not very prudent with his phone, so it's only 3-letter passcode. Okay, so what are you going to do? You have a stopwatch. You're going to make a couple of guesses, and you're going to time it, right? Start with the letter A. I mean, it immediately terminates, right? It's a 3-letter password. Oh, and let's pretend you don't know the length of the password. I'm going to tell you it's 3 letters, though, because I know. So you guess A. I don't know. It runs for some amount of time. You know, you don't really know anything beyond that. You try AA, right? Okay, that still just runs for the same amount of time. And then you try 3 A's. Okay, and hey, all right, it runs for a little bit more time, right? Why? Because remember, the first thing that you did, that the code does, is it checks the length, and it early terminates. So the fact that it takes more time with 3 A's means at least you passed the length check. All right, so we're getting somewhere. So we know it's a 3-letter password now, all right? Time to start guessing letters. Well, we know it's not AAA, otherwise the phone would have just unlocked, right? Okay, so let's start going through each of the letters. Let's tweak the first letter. BAA. Okay, cool, another spike. That means we got a little bit farther in the program, right? Good to go. All right, let's try, that means that first letter must have like clicked into place, right? So now let's start twiddling the second letter. BBA. Okay, the timing actually went down a little bit, right? We got worse. It terminated earlier than we would have expected it to. What must have happened is that BA was the first 2 letters of the password, right? That's why, and then so when we change the second letter, now we're only 1 letter correct. So let's go back to doing 2 letters. It's BA something. BAB, I don't know, we're kind of back to square one. It's about 2 letters in. Try BAC, BAD, all the way up to BAS, right? Again, no change in timing. Finally, you try BAT, and the timing, it would take the most amount of time, but I think more telling is that you've unlocked your friend's phone. Congratulations, you've hacked your friend. Shame on you, but congrats. So again, this seems like a very cute example. No one really actually writes password checkers like this, right? And it seems sort of easy to defend against. But there was this really seminal paper by this guy Paul Coker. I mean, this guy, he's a very famous security expert. And he basically did timing attacks on various security. Oh shit! Sorry, shouldn't have said that. He did timing attacks on various cryptographic primitives, right? Like on RSA and stuff. And the idea was that if the amount of work that these security primitives do is a function of any secret bits, you just time the thing and then you do like a lot of sophisticated analysis to try to reverse engineer what the thing is. And again, it's if you actually read that paper, it's like it's kind of, there's a lot going on. It's not as simple as our little password checker, but the point is that it can be done, and it's something that you have to take into account when writing cryptographic code. And then the second paper showed that, like 7 years afterwards, it showed that not only are these timing attacks like doable, you can do them on a remote server, right? So even if somebody else is hosting cryptographic code, you can go and attack them, which is typically the environment you're dealing with, right? Like you're not running your own cryptographic code, you're attacking somebody else's. So, what do we do? Timing attacks are a problem. Well, we'll do something, we'll start writing what's called constant time code, all right? And the goal is just to make the timing of the program independent of the inputs of the program, right? And it really kind of just boils down to don't branch on secret values, right? I mean, look, if you have a branch on a secret value and you have one fast path and you have one slow path, it's kind of obvious, just like time the paths and you know which one you took. And since the branch is the function of a secret, the branch direction tells you something about the secret, right? So in essence, what you want to do is avoid code like this, right? Where you say, if secret, do a slow task, otherwise do the fast task, and that's your result, right? And going back to our password checker, you can see these are the secret-dependent branches, right? We're comparing the lengths of the passwords. That's like a function of secret information. And then we're also just comparing the characters directly, also very much a function of secret information. These are secret-dependent branches. This is not good constant-time code, all right? So what are you supposed to do? Well, what you do is you write like your code in like a straight line fashion, right? So even though there's a fast task and a slow task, if you just do them both, it's going to take the same amount of time no matter what. How would you do such a thing? You just, what the heck? Well, that's, okay, all right. What was I gonna say? Oh, right. Yeah, so you compute the fast task and the slow task, and then you just select between the results at the very end. A little bit of a caveat here. I'm using like the ternary operator from C. You got to make sure that it doesn't compile to a branch or you're back to square one. You want to use what's known as a conditional move instruction. If none of that means anything, just ignore all of it. In any case, how do we use this philosophy for our password checker, right? Let's remove the secret-dependent branches. So the initial stuff is the same. Get the username, get the password, get the real password from the database. Now what we're going to do is we're going to use the XOR operator to be like smart about comparisons. And the key is that when you XOR a value with itself, you get zeros, right? So first thing we'll do is let's XOR the lengths together, right? And we'll call that result, right? And we're going to shift it up 8 bits. Why? Because we're going to start XORing characters and put that result in the lower 8 bits, right? So the upper 8 bits will be 0 if the lengths are the same. If the lengths are not the same, the upper 8 bits are going to be, I don't know, some non-zero value. So now we go character by character and we loop through and we just XOR corresponding characters and accumulate them in the lower 8 bits of the result. And then at the very, very end, we check if the result is 0, right? If the result is 0, it means the lengths must have been the same and every pair of characters must have been the same, which means the passwords match. If anything at any point went wrong, the result would be a non-zero value and we can just say wrong password. Yes. Oh yeah, you're right. Oh well, good catch. All right, I think, yeah, no need to shift. Yeah, okay, all right, forget the shift. Just put everything into result and you're good to go. Nice. There still is a problem here though, by the way. There's like a subtle, like this isn't actually 100% secure. Does anybody see like the slight leakage that you can get here? Yeah, so I don't know if everybody heard, but basically what he said was, since we're taking the minimum of the lengths, you can just try passwords of different lengths, and like if your guess is shorter than the password, you'll notice that like the longer your guess is, the longer time it will take because you're the minimum, right? But the minute you become longer than the actual password, your timing will saturate because now the real password is the minimum, and as you guess longer and longer passwords, your timing stays flat. And so like at that like tipping point, that would tell you what the length of the password is, which isn't like that helpful. I mean it's better than nothing. It does simplify your brute force search. especially if it turns out they only have a 3-letter password. But the point is, this is not very secure. Also, a little side note at the bottom here, don't actually check your passwords this way. In reality, what you're supposed to do is your database is only supposed to store hashes of the passwords, and you're supposed to like hash on the client side, send that over, and compare the hashes together. You shouldn't be storing raw passwords. That's like the safe way to do it. I'm sure there's like 100 other things you're supposed to do that I don't know. So anyways, we're done, right? Like, okay, we have our little constant time principle, right? Just don't branch on secret values and you're good to go. What could you possibly learn from the behavior? Well, it turns out, no, we're not done because there's like a lot of time left in lecture. I didn't just plan like a 10-minute thing here. So it's really this guy that's about to ruin our whole lives, the CPU. So now we're coming back to kind of what you were trying to hint at. The CPU is not really going to be our friend in this scenario. And you really can't trust anybody, right? The thing is that like you can have code that looks side channel free, right? You can like write nice code, but you run it on the actual hardware. You inevitably end up with data dependent observations, right? It's kind of like the environment in which you do something really affects the thing, right? It's like building like an ice sculpture in like a greenhouse, right? Like as good as you are at it, the environment is working against you. And it's kind of our fault, and when I say our, I mean, I guess like whoever makes CPUs. We want, actually, no. By ours, it seems like it's ours, the consumers as well, so it's all your fault as well. We all want computers to run faster and faster and faster, right? That's like the #1 benchmark, right? And here's the thing, CPU designers, like if they're trying to crank out like performance numbers, they're gonna take shortcuts. They're gonna do like neat little optimizations, right? And those shortcuts are going to end up data dependent, right? And I guess now I would be remiss if I didn't show the graph that everyone ever in the architecture community likes showing every time they give a talk. And this basically just shows that Moore's law is dying, right? I don't know if anyone's familiar with that. Just to cover it, Moore's law was like this like thing that Moore coined way back in the day. He's like, yeah, I think every 18 months the number of transistors on a chip is gonna double. And that's sort of actually held for the longest time. Although people think that the reason it held is because Moore set a benchmark, right? It wasn't a natural thing occurring. Everyone was just like, damn, we better start doubling transistors every 18 months or we'll look bad at our jobs. Unfortunately, that's sort of like, again, if you go to any talk by any architect ever, they will say the words Moore's law is dying. And I would bet my left arm on that because it is. And so the number of like transistors you can cram on a chip is sort of, again, like going down. You don't get that performance benefit for free. You're gonna do a lot more exotic optimizations. And so, yeah. So in any case, how can CPUs break secure code, right? Like what are they doing under the hood? Well, there's two major ways they can break your code, right? And this first one is like, I think this first way is kind of, I think, the most like intuitive way, but it's also not a very common way. So without further ado, what is it? Well, some instructions can take different times depending on their inputs. And I mean, that kind of makes sense. Like we've been talking about like, those weird boxes and based on the color of jewels, they take different time. This is the same thing, just at the instruction level, right? So imagine you write your program and you are security conscious and you take into account, well, I shouldn't branch on secret values. Let me do this straight line code. Great. You compile it, it turns into a program, and it takes some input. Awesome. Well, it turns out that green instruction there in the middle, well, the second one, hopefully no one's colorblind, but that second instruction there, depending on the color of the jewel that you toss into it, right? That green instruction could go very quick, or it could go very slow. Oh, well, now you have a timing or input-dependent timing difference. There you go. You're going to leak something, right? And you might say, well, what sort of instruction would do such a thing, right? The very simple example would be like a zero-skip multiplication, right? So suppose your CPU has an optimization that it says, okay, I send a multiply instruction to the multiplier, right? And it detects, okay, well, one of the inputs is 0, right? One or both is 0. I'm not going to bother doing the multiplication, right? I'm just going to go ahead and say the result is 0 because, as we all know, 0 times anything is 0. And so, that tells you something. If you time the multiplication, it tells you if one of the inputs is 0 or not. So, but yeah, like I said, these leaky instructions are like far and few in between, right? So there's this one paper in 2009. It looked at early terminating multiplications, and it found that it could break certain like a bunch of different cryptographic protocols that were implemented on it. The catch to that is they were looking at like embedded processors, not like CPUs. So So that sounds weak, but with the advent of IoT, right, like these embedded processors are everywhere, and I think that paper goes to show there's an old adage, the S in IoT stands for security. In any case, there was another paper. This one was more interesting. They used subnormal floating point, the timing of subnormal floating point instructions, right? And with that, so subnormal floating points are just like floating point numbers that are very, very close to zero, out of the normal range, right? And based on whether you compute with those or normal floating point numbers, the timing of the multiplications and stuff changes. And so this paper actually did a really cool thing. They did like a pixel stealing attack. Like you load some external website into an iframe. You use like Mozilla Firefox SVG filter, and you can basically just steal the pixels from like a website that you don't actually even have access to. So again, but these types of instruction-based attacks are not super common. You don't find like a lot of these kind of things, right? The big one is that shared resources allow an attacker to snoop on the activity of a victim. So let's say you have some shared resource here, and you have the victim and the attacker, right? And let's say the victim wants to use the resource. Well, maybe while the victim is using the resource, the attacker cannot use the resource. This is contention, right? So the fact that the attacker cannot use the resource tells it something. It tells him that the victim is using the resource, and maybe that conveys some information. The other thing is that maybe it leaves some footprints behind, right? So in this case, the victim seems to have left a letter and like tipped that little flag up, right? And maybe the attacker can't quite see the. All right, well, maybe the attacker can't quite see the letter itself or read its contents, but it sees the flag is up, right? That's like a footprint that it left behind. And again, maybe that tells it something. And again, like I said, this is kind of like the big way that you can leak information via side channel. So let's talk about a specific shared resource. This is like, I think like kind of like shared resource numero uno, caches, right? This is not an architecture class, so I'm just going to go through the description of a cache anyways. So you have the program and you have main memory, right? And memory is where all the data lives, and the program wants to, do stuff with the data, like compute it or whatever, right? And so it'll go ahead and it'll send a bunch of reads to memory. It'll get some data back. Maybe it'll send some writes, whatever, right? This takes forever. Like the latency from the CPU to like RAM is exceptionally high. And really nobody has time for this, right? Like we consume so much data, we do so much computing, this would absolutely, you'd never play Minecraft again, as I'll just how I'll put it. So what we'll do is we'll put a little block of memory very close to the CPU called the cache, right? And the thing is the cache has to be quite small. It's got to fit on the chip, but it's close, right? So when you read and write to the cache, well, that's super quick, right? It's like right there. Great. Occasionally, like again, the cache is like a finite thing in size. Not everything will be in cache. You'll kick stuff out of the cache. You're going to have to go to main memory eventually. And that's going to take forever. There's really just nothing you can do about that. The idea is that that should rarely happen, right? It's a simple expected value, right? High probability you hit in the cache times low latency. Low probability you have to go to main memory, high latency. Hopefully that expected value, is pretty low. Depends on the probability of things being in the cache. It turns out things are really good at staying in the cache. So that's why every CPU has a cache on it, right? But security-wise, I'm sure you see the problem, right? We now have a slow path and a fast path in the system, right? And the adversary can exploit this fact by showing up with a timer. Okay, so we know there is a slow path, we know there is a fast path, but the question is how would you like particularly exploit it, right? And that's like the key. So let's talk about a very simple cache attack, right? It's called prime and probe. Very easy to understand. So we have our processor, right? And then there's a cache in it. And let's just say it's got like 4 little blocks that it can store data in, right? So first, the attacker goes first, right? So what they do is and then there's like a victim waiting on deck, right? So the first thing that happens is the attacker primes the cache by filling it with its own data, right? It doesn't actually matter what that data is. It's just trying to occupy those cache lines, right? Now there's a context switch. The victim comes in, right? Now they go ahead, they're just doing their thing, right? They, like they load something, right? It needs to go in the cache, right? Now, again, like I said, the cache is a finite space. If it was full before and something new comes in, something's gonna have to go out. So you know what? It goes ahead, it evicts like that third cache line there, right? And now the victim's data is there. Okay, cool. Now there's another context switch. The attacker is back, right? They're running on the processor, but they bring a timer with them, right? And they try to access their old data, right? So they're gonna go they're gonna go access everything in the cache. Now, if they access a cache line that their data is in, that's the fast path, right? It immediately loads it. Great. So those first two cache lines and that fourth cache line, it goes very quick. Their data's still in the cache. What about that third cache line? Well, what'll happen in the CPU is the attacker will issue a load. It'll go to that cache line, and it'll say, well, this is not your data, right? So we're gonna have to go all the way to main memory and like get the real data. And that load is going to take a very long time, right? And this is the attacker probing, right? It's probing each cache line and timing it, okay? So the thing is, like, the attacker can't see inside this cache line, right? Like, the processor won't let one process load another process's data. That's like horribly insecure, and So, but what it does see is that the victim touched that cache line, that it evicted that cache line, right? And it knows the location of that cache line. And without getting too much in the weeds, sort of the way caches work, in CPUs is that when you load from a certain address, like which particular cache line that load goes to is a function of that address. So if it can see which cache line got evicted, it knows something about the address. So now, if that address depends on a secret value, the location of the cache line depends on a secret value, and the attacker has just learned that secret value just by looking at which cache lines get kicked out of the cache. And again, it's about there being a fast path and a slow path, right? And people have shown that you can use these cache attacks to like attack AES implementations. So again, AES is just an encryption thing, and there's so what AES like kind of in a nutshell, there's like several rounds that you apply to a plain text, and you throw some key in there, and you get out a ciphertext. It turns out you can like squash a lot of these rounds together into what are called like T tables. All you need to know is those are like lookup tables, and you look into those tables based on the key, and well, okay, so now you have like memory dependent or secret dependent memory accesses. So like the pattern of like cache lines you kick out tells you something about the key. And again, it's a very sophisticated like attack. It's like not as easy as the cartoon shows, but it's interesting for sure. And then I mentioned there's another way, right? So that's like the footprint-based approach. There's also like a contention-based approach when it comes to shared resources, right? So I don't know if you guys know what SMT processes are, simultaneous multi-threading. The idea is that like instead of running one program at a time, you kind of double the data path, and you can run two programs at a time. And those programs have, some of the resources of these programs are separate. Some of the resources are shared between these simultaneous threads, right? Particularly like the functional units, your adders, your multipliers, and whatnot, right? But of course, a functional unit can only do one computation at a time, right? So if while the victim is using that functional unit, the attacker cannot. And again, maybe that conveys some information. Or maybe you have like several processors connected by a bus, right? Victims on one processor, attackers on the other processor. While the victim's using the bus, the attacker cannot use the bus, and maybe that conveys some information. And there are some papers that have like done this. Like so, the Port Contention for Fun and Profit, great title by the way. That paper, it like attacked I think like some elliptic curve cryptography thing. I don't know this. But the idea was like that the operations that the primitive did, right? Whether it does like a certain kind of multiply or not, depends on a secret value, right? So what the attacker can sort of do is just like flood the functional unit with its own dummy multiplies, and then see does the victim run slow or not. And that tells it if it's trying to use the multiplier, right? And if it's trying to use the multiplier, that tells it something about the secret. And then the second paper was actually one of my lab mates, Chris over there is my advisor. That was a Lord of the Rings. They did like there's like a ring bus that connects all the cores together on Intel chips. they reverse engineered how that bus works. And basically, again, usage of the bus was dependent on some secret, and they attacked some cryptographic primitive, right? So, all right, bleak picture. It looks like shared resources are hell on earth, right? It seems like we're kind of screwed here. Is there something we can do about it? And yes, there is. And we'll consult the Lord of Security here. That's just a wizard. I couldn't find a god emoji, I think, because that's blasphemous. But in any case, the first commandment is thou shalt not branch on secret values, right? So we've covered this one already, all right? The second one is thou shalt not access memory using secret values. And that one, it comes from the cache stuff we talked about, right? Again, the cache is a shared resource. Do not use secrets as memory values here. And finally, there's thou shalt not pass secret values to data-dependent timing ops. That one's kind of a mouthful, but again, that one's sort of like the obvious one, right? It's like, this was like what we talked about way back. Certain instructions might run slow or fast depending on their inputs. If you know what those instructions are, don't use them. Again, fortunately, those are far and few in between, but the idea is that, look, if you obey these 3 commandments, right, you should never have problems again, right? That is, what could possibly go wrong? There's a little bit of a side note here. Your compiler can work against you. You can write code that looks constant time, and your compiler in its respectable goal of making your program run as fast as possible might change how your code gets because you'll write it in C, right? But then it turns into assembly. It'll play some tricks along the way to try to get it to run faster. And these group of researchers found out that a lot of well-known security libraries, what would happen is that if you run it through LLVM compiler, a lot of constant time code would suddenly become non-constant time. It would add branches where there shouldn't be. It would try to combine instructions when it shouldn't and all that stuff. And look, but to be fair, the general principle still holds, right? This seems like a very solvable issue. It's just an engineering thing. You just have to tell the compiler, please don't do it, right? Or heck, hand roll your own assembly, right? Do that. And then, but it still seems like we should have no problems with the constant time principles. The answer again is no, again, because I still have I think 20 minutes. And so, the CPU is gonna come back again, right? And this time it's gonna come back with probably the 2 biggest villains in process security, right? Spectre and Meltdown. You might have heard of them, right? We're not gonna talk about Meltdown. It's kind of like Spectre-esque and I don't have time. All right, well, let's talk about branch prediction. This is kind of an important architecture topic. We'll talk about it at a high level. So you got your program, right? And it comes along a fork in the road, a branch, right? Do I go left? Do I go right? He doesn't know. Well, he'll know eventually, right? But it's gonna take time to know. And we wanna compute now. So what we'll do is we'll consult an oracle, right? And this oracle will tell us which way to go. It's like guessing, but it's pretty accurate, right? And it says, you know what, go ahead, go left. So let's take the left path and we'll start doing those computations, right? We're speculatively executing here, right? Now, eventually we might find out, okay, we weren't actually supposed to go left. We just did a bunch of work that was wrong. What do? Well, we squash, right? You flush the pipeline, you clean up registers. Basically, you undo everything you did, right? So it's almost like it never happened. And then you just go ahead and do the correct thing, right? And to you as a programmer, and then maybe you encounter another branch and you do the whole thing all over again. You as the programmer, you don't see this speculation happening, right? To you, the program is always doing the correct thing. This speculation just sort of happens, under the hood. The question is, I guess then, how does that give you a performance benefit? Well, if we hadn't squashed, right, by the time the branch resolves, you'd have gotten a head start, right, on that computation. Like the branch would say, oh yeah, go left. And you're like, way ahead of you, already did a bunch of things, right? And if you're right most of the time, that's a pretty big win. And here's the problem. I said squashing is like cleaning up, right? Like make it like you were never there. It makes it, to the programmer, it makes it look like it was never there. But that doesn't mean that it perfectly cleans up the scene, right? There are some traces left behind that the program did go down that path, right? And that's sort of where we're gonna start seeing the security issues. Now, the question is, look, this only happens if you go down the wrong path, right? But if you look if you look at how accurate branch predictors are, they're really freaking accurate, all right? Like, I mean, like they ran it on some benchmarks, like state-of-the-art branch predictors. The average was like 95.2% accurate. On one of the benchmarks, it was 99.7% accurate. I've never been 99.7% accurate on anything in my life, so they're doing really good there, all right? So if the wrong thing rarely happens, how can there be a security issue, right? Like you never mispredict, right? It's not that simple, because this is like the branch predictor being left alone to do its job, right? It turns out predictors can be pushovers. And I'm not going to go into the details of how exactly this works, but basically you have a program and you have an attacker, right? And then you have like this branch predictor. And like, you know, you're querying the branch predictor. You're saying, all right, which way should I go down the branch? And the attacker basically has the ability to say, you're going to say left. It's going to tell the oracle what answer it's going to give, right? This is known as mistraining the branch predictor. And you know, the oracle will just agree. It'll say, all right, yeah, sure, why not? Left, you know, and then the programmer, again, the programmer's not going to do anything about it. The oracle said go left. What's it going to do? Say no? No, it's going to go left. So the attacker can kind of force a mispredict, right? So just because branch predictors are really accurate, you know, that doesn't actually stop any of this thing. Again, grossly simplified, but it really doesn't matter. All right, so now let's talk about bypassing the bounds check. All right, Spectre v1. We got the registers, we have cache, and we have memory. We got our branch predictor oracle, and we have the Spectre gadget, right? What does it do? It has some input X, which will actually be provided by the attacker, and it checks if X is inbounds the array A. If so, it gets Y. And it uses Y as the index into array B, and then it gets Z, right? And I've colored array A red there in the memory and array B blue in memory. We got the program, and of course we got the adversary. And you know, all right, it's all coming together, all right? Let's see what happens. So first things first, the attacker's gonna prime the cache, right? Then it's going to supply its own particular value to X, right? And again, it is allowed to do that. We're assuming that this gadget is constructed such that the input comes from an external person. The external person just happens to be the attacker. All right, well, what happens? All right, well, we have this branch, right, that says, okay, all right, let me make sure that this input is inbounds before I just use it to access this array A, right? Prudent, great. The attacker is going to just ask the oracle to say true, right? And the oracle is going to say true. It's a pushover. And the program's also a pushover in a sense, and it's just going to go ahead and listen to the oracle. It's going to say, okay. So even though X is just some arbitrary value, we're going to go ahead and use it as an index into array A. What does that mean? Well, we're going to essentially, when you index an array, right, you just add X to the base of the array, and that's the address you load. So if they provide the right value of X, they could go ahead and load that secret value way out in distant memory, right? And so they go ahead and do that. So now the secret value gets loaded into memory. And you know, anything that's loaded from memory also gets brought into the cache, right? So it's sitting there in the cache. Great. Now we have our value of Y. And again, Y is equal to that secret value. Now let's use Y as an index into array B. That's going to load just some random value from memory, right? Like secret is going to be some arbitrary value that we're just adding to base B. I don't even know what's there in memory. Could junk, essentially, right? And we're going to load it, and we're going to put it into the cache, right? But particularly the address that we're using to load is B plus secret, right? And so the specific cache line that got evicted there, remember, the cache line that you go to depends on the address that you load. So that cache line that was loaded depends on what the value of B plus secret is. And if you assume that the array base bounds are known, that means it's a function of secret. That'll come into handy, right? Now, eventually the process says, okay, wait, X was not in bounds, squash, undo all that work, right? And it'll rewind back to the point of the branch. It'll clean up the registers, right? Because again, it has to undo any computation it did. It should look to the programmer that it did nothing wrong. It does not clean up the cache. The cache lines that were present or evicted, they stay the same, right? So now this is where the attacker starts probing, all right? It's gonna time its access to the cache lines. Because remember, the cache was originally filled with all its data. Some of it got kicked out and got filled with the victim data. And it doesn't get to see the victim data, but it does get to see if its data got kicked, if the attacker data got kicked out. So it times all these lines, and it sees that that particular line takes a long time to load, must have been kicked out by the victim. And remember, that line was a function of secret. So just by seeing the location of that line, it learned something about the secret. And that's essentially how Spectre variant 1 works, right? And that's why it's called the bounds check bypass. Because you misspeculate past the bounds check, load an arbitrary value, do something with that arbitrary value, and then that's what leaks the data. There's this one guy, David Kohlbrenner, who we collaborate with. He told a fun story. So it's anecdote time. So they were like, people kind of like, he was saying that like people kind of knew that like branch misspeculation was gonna like lead to, you know, that you could go down and maybe touch secret data that you weren't supposed to. But they were really struggling to get it to work, and they were convinced that, okay, the idea seems feasible, but you just can't construct an attack. And it's because they were only considering a single load. It was only much later that somebody else considered doing a double load, right? So, because the idea here is that the first load is like what you can call an access. It brings secret data into the core. The second load is the transmitter. That's the one that actually like leaks the data. So, you know, and then eventually someone did try out the double load, and, you know, worked out really well. It was a really famous exploit. And you know what? There's so much speculative execution attacks out there. It's absolutely crazy. It can also like look kind of overwhelming. There's like 100 of these, and they give them all these like fun names. And I feel like nowadays, every time you come up with like a microarchitectural attack, people spend a significant amount of time coming up with logos for them. Like they all have logos now. It's weird. But yeah, I mean, it's kind of like a choose your own character type of situation here, where like, honestly, if you understand Spectre v1, you'll probably get all the other ones, right? You just sort of change the parameters, right? So you might change what kind of speculation you do, right? You might change the specific channel that you leak through. In Spectre v1, the channel was the cache. There are papers that use port contention, the return stack buffer, any sort of shared hardware resource sort of works. But it all comes down to the same thing. Go down a path of the code you weren't supposed to go down. Leave something behind, come back later, find it, and that ought to tell you something. Now the question is, okay, all right, so Spectre attacks, they're crazy, they're scary, right? How do we fix them? Well, there's sort of the straw man approach, right? It's pretty simple. If speculation is the thing causing the vulnerabilities, why not just, just disable it? Yeah, so the problem there is, remember I showed you the stats on branch prediction. Branch prediction is really freaking accurate, and it is like one of the pillars of modern processor performance, right? You will not convince anybody to get rid of speculation. And there's this like pithy quote I heard once. It was, we do not feel justified in giving up what has come to the industry like a gift from heaven on the possibility that a hazard may be involved in it, right? Very pithy quote. Unfortunately, that was like the Standard Oil president defending leaded gasoline, but, you know, but good with words, ain't he? So our goals for our cake here are we want to have it and eat it too, right? So we're not giving up speculation, all right? So what can we do? Well, there's like a dumb software approach, right? The second easy thing we can do is prevent speculation selectively. That's a tongue twister. Right? Just do it in the problematic spots, right? Look, not every branch is like evil. Not every chunk of code is going to leak something sensitive. If you know where, you know, the crazy spots are, just stop it there. And to that end, there's like a certain instruction on x86 processors you can use. It's called an L fence. Basically just doesn't let you speculate past that point, right? So this is, again, what the Spectre v1 gadget looks like, right? And, you know, the way the barrier works is like, you know, when it comes across the branch, it hits the barrier and it says, I'm going to wait. I'm not going to guess. I'm not going to do anything. I'm going to stall. I'm going to wait to see where the branch should go. And then it'll proceed if, you know, in the correct direction, right? So in the Spectre v1 example for the bounds check bypass, it's going to wait for the bounds check to resolve. We're going to make sure that the attacker provided value is in bounds of the array before we just start loading things willy-nilly. You know, the problem with this, of course, is that, like I said, speculation is really important to processor performance, and there can be a lot of locations where you have these Spectre v1 looking gadgets, right? And so I think I heard from some guy at Intel once that, like, I don't know if I'm supposed to share this, but if you look at like the Windows 11 source code, it's like apparently like riddled with these L fence instructions, right? And operating systems particularly have to be sensitive to these sort of things, right? Because like the operating system controls everybody's data, all programs' data, right? It's a really high value target. So it has to protect itself by all means necessary. So odds are they probably did throw in a lot of LFENCE instructions in there, right? And that's going to cause some slowdown. There's a more clever software way. It's a really nice trick. I actually really like it. So there's a thing called speculative load hardening, right? And this is what the LLVM compiler does. And this is like, they came up with this like pretty soon after Spectre came out, I think. And basically what you do is you tie the loaded value to the branch predicate via a data dependency. And the trick is you can't speculate past data dependencies, right? So here we again have the Spectre v1 example. And in red, I've shown kind of the new stuff we've added, right? So we do this first load, right? We load using X, and we get a value Y. And what we do is we just have this value Y prime that selects between, well, the original Y or just all zeros based on the condition, right? And then we use Y prime as the input for the load to Z instead of the original Y. How does this help us? Well, so this is what the control flow graph of the program looks like, right? There's a condition, and there's a good path and a bad path, right? And the bad path will lead you, like, you know, sort of to the speculative region which we do not want to go. And this is what the data flow graph looks like, right? This is X is the input to the load. The output of the load is Y, which is the input to a select instruction, which also takes in the condition as another input. Out of that select instruction, you get Y prime, and that Y prime is fed into the load, right? And again, it's that second load that's kind of the problem, right? That first load just gets the secret value. That second load is what like leaks it through the cache. Okay, so what happens? So we're going to assume that we're speculating past the condition. We don't know what the condition is, right? And the processor is very eager to speculate. Now, as far as the control flow graph goes, right, which path through the program you take, what sequence of instructions you're loading, the processor will go ahead and speculate. It'll fetch, decode, and execute what it thinks the correct instructions are, right? But what about the data flow graph? Well, we have X, we'll do the load, and we have Y, right? But what we'll find is that that select instruction blocks the data flow at that point, right? Because again, we passed X to the load and we did get Y. One of the inputs is ready, but the other input to the select instruction, the condition, is not ready, right? So until the condition is ready, the data flow graph can't proceed, which means that secret value Y can't physically make its way to that second load, right? So again, the key point of speculative load hardening is you use a data dependency to prevent the speculation in this case, right? And that does a lot better than barriers. It's still like pretty high overhead, but again, a very clever way. And then of course there is sort of like the hardware way, right? Where you just sort of like change how the processor is architected to, you know, speculate securely, make sure secret data doesn't make its way to transmitters, or just block speculative transmitters. There's like so many of these papers that, you know, you could spend your whole life reading them. Yeah. This one. No, this is a victim gadget. The attacker provides the input X, but it's the victim. So, oh yeah, so maybe that's really worth clarifying. So the Spectre code is, for Spectre attacks particularly, the code is the victim's code, right? You are trying to trick the victim to do something. The attacker just provides like a malicious input. So yeah. And then, yeah, and so, yeah, a lot of hardware papers, you know, and the thing is, like, so there's like a paper a couple of my lab mates and like my advisor did way back, and basically what they did is they went through the literature and they looked at like all sorts of microarchitectural optimizations, right? And they said there's a lot of novel ways to leak data using all these optimizations, right? Like even just beyond speculation and all these sort of things, right? And basically, again, it comes down to that idea of we want faster processors. We're going to use more and more exotic optimizations, and these lead to novel security implications and whatnot. So, you know, as I said, though, if you're going to hardware security research, a lot of money out there, you know. So yeah. So anyways, so that's sort of the end. And I guess you know, I think maybe people have heard of the pithy quote, right? Like those who would give up essential liberty to purchase a little temporary safety deserve neither liberty nor safety, right? by our very own Benjamin Franklin here. There's sort of a variant, I guess, that applies to processor security, right? Anyone who'd give up security for a little performance deserves neither security nor performance. But if I could undercut the poignant tone of this a little bit, I remember I did an internship at, and my mentor there used to work at, and his mentor said, was telling him, oh yeah, like all performance optimizations, like you get like maybe 1%, right? Like that's where all the big fruit has been picked. We're going after the little fruit now. And supposedly he then followed that up with, yeah, I'd give up my left kidney for a 10% performance increase. So yeah, with that attitude, I think you will see what happens security-wise. And then, yeah, that's it. I have no more. I guess there's maybe time for questions. I don't know.